And I'm a coastal geomorphologist who works at the University of Melbourne. And so I'm originally from New Zealand, and I moved here in 2012 to do my PhD on estuaries on the southwest Victorian coast. So over the last almost 10 years or so, I've worked a lot on these systems around Victoria. I have not done a huge amount of work at Curdies. It's always kind of been a site that I wanted to work on, but until recently, a couple of years ago, wasn't able to get out there. But I have recently, and I've got some really exciting data that we collected in the field, which I'm going to show you guys. So today I'm going to talk first a little bit about the physical processes of Curdies Inlet and estuaries that close in general. So things that control opening and closure of the entrance and the movement and exchange in sediment and water in and out the mouth. I'm then going to talk a little bit about why Curdies Inlet is different to other estuaries in southwest Victoria. And then lastly, I'm going to share some of those results I mentioned from our recent work at Curdies. So first of all, just to give an overview about estuary entrance processes. So Curdies Inlet, like lots of other estuaries in Victoria, is one which has an entrance that opens and closes. And so whether the entrance is open or closed is a function of competing forces. So first of all, just looking at the closed example here. So we have from the ocean side, waves, which are working to move sand onshore and alongshore. So waves are transporting sand onshore and trying to close the entrance. And then on the other side of things, from the catchment, we have river flow coming down to counter that. So when these estuaries close off, it's when we have higher wave energy than river energy coming from the catchment side. And so that wave energy is high enough that it can push sand onshore and infill the entrance and build a beach berm. On the other hand, when we have an open entrance, this kind of ratio of energy is flipped around. So we have higher river flow relative to wave energy. And what that does is it has enough force behind it to push sand from the entrance channel and erode it offshore. But another factor that's quite important as well, and Curdies is a really good example of this, is something called the tidal prism. So the tidal prism is the volume of water that we see exchanged in the lagoon over each tidal cycle. So you can see that in this picture here. At high tides, the water elevation will go up and we see the influx of this volume of water. And then at the low tide, that will all go rushing out to the sea. So the tidal prism is a function of how big the basin is and also the elevation of the tidal range. So if we have a bigger tide, we're going to see more water go into the basin. And how this relates to entrance opening is when we have the outgoing tide, that's called the ebb tidal prism. So like our ebbing tide. That's essentially a force that's going to work to erode sediment from the entrance. So we can see that volume of water trying to push its way out the mouth and trying to move sand offshore with it. But what also gets added to that is any outgoing river flow. So our river here is pumping in water as well, that's going to add to that outgoing volume. And so when we have higher river flow and a larger tidal prism, that increases the relative energy of water eroding sediment from the mouth. And because Curdies Inlet has such a big basin, it has a really large tidal prism. And we'll talk a bit about how that impacts on the entrance opening duration in a minute. But just to summarize, whether the entrance is open or closed is really all about these competing forces working at the mouth. We have from the catchment side here, our river flow and our outgoing or ebbing tide. It's trying to push sand offshore. And then to counter that, coming from the ocean, we have onshore sand transport by waves. So those factors, the variability between river flow, wave energy, and the tidal range are really what drives the global distribution of estuaries which open and close. So I'm just going to zoom out to this kind of global context for a second, and then we'll look a bit more specifically at Curdies. So in terms of where these estuaries are found around the world, there's over 1,400 of them. So they're actually a bit more common than people tend to think. And they're always located on coasts where we have high wave energy. That's because consistent high wave energy is needed to move sand onshore and close the entrance. So in a global context, we see these estuaries situated on open coasts in areas that receive quite large waves. So for example, in Australia, we only really see them on the southern coast and the lower southeastern coast. That's because that's the area where we get big waves pushing up from the Southern Ocean and parts of the Tasman Sea. They're also found on coastlines which have a tidal range under 2 meters. So that's our blue lines here, and that's also called a microtidal range. That's because if we had higher tides, that would increase the energy of tidal currents going in and out of the mouth. And that would mean that basically those currents would always be moving sand offshore and the entrance wouldn't close. And lastly, estuaries that close are found in catchments with low or variable rainfall and also river flow. That's because they need those times where we have lower river flow in order for the entrance to close off. So thinking about the physical setting of Curdies, so just starting with the marine setting. So first of all, it's located in a very high energy coastline. Our average wave height is around 3.3 meters. So that's really high by global standards. And this picture here is showing a wave rose. So this is the direction the waves are coming from, and then the different colors are the wave heights. So that's from about 30 years of data. So we have pretty high waves happening all year round, but also we have waves coming from a really consistent direction. So here they're always generally coming from the southwest. And so we can see that in the picture here, waves coming from the southwest are coming onshore, kind of changing direction a little bit, moving in between this offshore reef, and then depositing sand at the mouth of Curdies. So thinking about that balance between wave energy and river flow and how that impacts on whether these estuaries are open and closed. So Curdies has both high waves and high river flow occurring in winter and spring. So our top figure here is showing the average monthly wave height, and the months are down the bottom here. So wave heights start to pick up around June and are quite high through till October. But at that same time, that's generally when we see our higher river flows. So thinking about summer, just because that's kind of a bit easier to explain, we have low flows in the river and we have pretty moderate to high wave heights. So a lot of the closures will occur during summer and persist throughout that earlier part of the year. But thinking about openings, we see an increase in both river energy and wave height. So it's a little bit harder to predict, and it really takes drilling down into the kind of specifics about energy balances between those two processes. But broadly, we see the estuary be open during winter and persisting sometimes even through to the end of the year. So we have strongly seasonal entrance openings and closures at Curdies Inlet. And this is just a time series of water level with the closures shown in grey and open periods shown in white. So this is taken for the whole year of 2019. And I just picked this because it was quite a good year to illustrate that point of seasonality. We saw an opening in June that didn't last for a super long time and it closed off again, probably due to a storm event or high waves. But then we saw another opening and the system stayed open right through until nearly the end of the year. And then during our close periods, so summertime closures that you can see in this picture there, we actually see a decrease in our water level in the system. And partly that's due to evaporation. So we have warmer water and the loss of water in the lagoon due to evaporating off the top. And water levels tend to pick up in autumn to winter, where we see an increase in river flow and the amount of water coming into the basin. So as well as physical processes, it's also important to think about the morphology of Curdies Inlet and why it makes it a little bit different to other sites in Victoria. So the morphology just refers to the form, kind of like the shape and the size of the estuary. So Curdies has a pretty large basin or lagoon behind it. It's about 3 kilometres squared, maybe a little bit under in water area. And that actually makes it one of the largest lagoon systems in Victoria. Because it has such a large basin behind it, that means that it has a large tidal prism. So that means that we see quite a big exchange of water over each tidal cycle. And when the system is open and we have high flow coming in from the river, as well as that tidal exchange, we get a big ebb tidal prism, so a big volume of water going out. And so that can mean that sometimes, under the right conditions, it can stay open for quite a long period of time compared to other sites. Another factor that sets it apart is that it has low infill. So what infill means is basically any sediment that's brought in from the river at this end or from the ocean side here. So forming this tidal delta that you sometimes see at the mouth under the bridge, that's infill coming from the ocean side. And these areas of swamp that are accreting and prograding into the basin, that's infill coming from the riverside. So a lot of estuaries in Victoria are infilled. So you might see a big floodplain with just a narrow kind of meandering channel cutting through that. And Curdies is one of the only few that really has such a big open basin. So this is just showing an elevation map of the surface of the land and underwater in parts of the basin here. So I just put this in because it really nicely captures that big basin that you can see here going around the outside. So once upon a time, probably about 8,000 to 6,000 years ago, we had sea levels come up higher after the ice age. So when all the snow and ice melted, that caused sea levels to rise. And sea levels at one point were about actually 2 meters higher than they are today. So they would have flooded out all this area. Sea level then kind of dropped down over the last 3,000 years or so to its present day level. And so that's brought the water area of the basin back down to here. But what you can also see captured in this elevation map that's quite interesting is at this area here, we also have a bit of shallower land. So it's a little bit hard to see, but if you squint your eyes, it might look a little bit more yellow or green compared to this blue area here. So that is basically infill happening. It's sediment, in this case, it's being brought in from the river and it's gradually settling out and shallowing the basin. So if we compare Curdies to the Eyre River just east, the Eyre River is an example of a system that's really infilled. So thinking back to what the basin would have looked like at a higher sea level, all this area of floodplain that's now infilled once would have been underwater. Sea level dropped and we had progressive infill of sediment coming into the basin over time. So as a result of both of those processes, the Eyre River looks really different. It has all these swampy sediments that have filled up that once large basin. And so that actually has an impact, we think, on how long estuaries will stay open for. So both the size of the tidal prism as a function of having a big or small basin, and also the amount of flow coming in that adds to the ebb tidal prism. So comparing those two sites, Curdies here with our red arrow and Eyre River with our black arrow there. Curdies has a really big basin and quite a big tidal prism. When we combine that with quite high flows over river, quite high river flows over winter, that means that relative to other sites in Victoria, it has quite longer opening durations on average. So that can span from less than a day, as you guys probably have seen, to months to nearly a year at a time. Our smaller systems here tend to have shorter opening durations. There are some exceptions to this rule, but it's just kind of a trend that we see across these estuaries. So having a larger basin area generally increases the opening duration. So just to summarize physical processes at Curdies, and in particular, what makes it a bit different to other estuaries. We have consistent high waves all year round. So for example, on the Surf Coast area, our waves are a little bit less energetic. Whereas at Curdies Inlet, because we're exposed to the open coast, we get really big waves all year. It's also quite a big river and catchment, one of the largest ones for estuaries that open and close in the state. We see a very seasonal pattern of openings and closures naturally. If you compare that to something like the Eyre River, for example, it opens and closes a lot throughout the year. The size of Curdies Inlet plays a role in how open or how long it is open for. So the large basin and large surface water area mean that it has a big tidal prism. And so that sometimes under the right conditions can keep it open for months at a time. So now to finish off, I'm just going to go through a bit of the recent research that we've been doing at Curdies Inlet and other estuaries in southwest Victoria over the last few years. So I'm going to talk about 3 key questions that all kind of have a link to management. So our first question we were looking at is what determines when openings will stay open past excavation. So openings are usually implemented when we have low waves and before periods of high rainfall. So kind of our ideal conditions to open up an estuary. Sometimes there are emergency openings, which just have to be done. But sometimes, even when openings happen during these ideal conditions, estuaries can close off again, sometimes within hours to days. So we're looking at why this might happen. And in some of our fieldwork in 2019, we captured a really good comparison at Curdies Inlet. So on the 16th of June, the estuary was opened at a wave height offshore of 2.4 metres, a water level of just over 1.33 metres. And what happened is it actually closed off a few hours after opening. It was then opened again the day after in the afternoon. But interestingly, this time it got really wide. The water really got ripping out the channel, and it was a good, strong opening, even though we had pretty similar conditions. So we're trying to look at what might drive these differences. And what we found is that the energy slope between the water in the lagoon and the ocean across the berm length gives a really good measure of whether openings will stay open past excavation or not. And so that's a parameter called the hydraulic gradient, or HG, but it's just basically the energy slope between the lagoon and the ocean. And that's a function of the head difference between the lagoon and the tidal height, and also the length of the berm. So just comparing between these 2 openings and potentially why one worked and one didn't, for the one that shut off quite quickly, it was opened over quite a long berm length and had a lower head, partly due to the tidal stage. The one that worked and opened really strongly was opened when we had a shorter berm, a slightly higher water level, but importantly, the tide was a lot lower. And it was opened on a falling tide too, which kept increasing the energy behind it. So there's a lot of considerations in practice that go into openings, and this is really just from a geomorphic sense, not taking into account things like fish and environmental impacts. But what we're starting to be able to do, thanks to some of the data captured by Estuary Watch, is we're able to go back through time and calculate that energy slope for a variety of openings and see where they fall out. And from that, start to get some thresholds that can guide, options of opening these when they will work potentially versus when they won't. And so just in terms of where our natural openings would fall out, These are openings which it's a bit harder to get data for just because of them not being captured. Natural openings would fall out in this high success area. So we need a high head for it to open, the berm would need to be short, and generally the waves would need to be low. The next research question that we've been working on is predicting how long these estuaries will stay open for. So both in terms of artificial openings and natural openings. And using that kind of idea that I introduced earlier, that the entrance state is a function of competing forces from the catchment side versus the ocean, we've been able to identify two variables that are able to predict opening duration. And so that's stream power, so basically energy from the catchment, versus wave power, which is a combination of the height and period of the waves. And so using records from EAMS and from Estuary Watch combined, we were able to go back and create some pretty good time series that pick out a lot of openings and closures. And in terms of those two variables, river energy or stream power and wave power, basically we created a ratio between the two of them. And then we averaged out that ratio for all the times the estuary was opening. So this is an example of an empirical data set. We're using real world data to pull out a relationship and then try to apply it. And just using that ratio between those two energies, we're actually able to pinpoint within a few days or so when the estuary will open, when it will close, and then how long it will be open for. So this red line is just the average from all these open periods, and we use that as our threshold. And so we wanted to test this in the field to see how good it was in reality. So taking that opening in 2019 at Curdies Inlet, the one that worked on the 17th of June, we applied this kind of predictive ratio. And so this is shown on the graph here. Here's our predicted lines. Basically what it shows is that under this red line, it means that river flow is dominating, and above it, waves are dominating. So here it was opened and followed by a period of strong river flow and erosion. So the entrance stayed open for at least this duration. And my last thing to talk about is what happens during an opening in terms of physical processes. So we went out to Curdies for their opening in 2019 in June, and actually monitored the change in channel width, area, the velocity or speed of the water flowing out, and the discharge, which is the volume of water going through the mouth. And so ideally, we're trying to compare a lot of data between different estuaries to try to see if they all follow a similar pattern. And that's important because it links change at the mouth, what's happening in the basin. So some of our initial findings, and this is just applying it to the data at Curdies, is that we get this initial period of pretty slow channel expansion and pretty slow outflow. At that time in the basin, not a lot is happening. We haven't seen a lot of drainage going on yet. That persists for about 2 hours, just on average. And then we enter this period of really impressive geomorphic change. So the channel's getting really wide, really deep, outflow is getting really fast, and that's when we see those big standing waves happening in the channel. And then lastly, it starts to level out. So from when we measured this in 2019, it took about 16 hours for the channel width to stabilize, for peak discharge to be reached. And after that point, it was maintained for an hour or so, and then it all started to drop down. And once that happens and the velocity stops going up fast at the mouth, that's when you start to see tidal influence. So tides bringing in water, and we see the fluctuations in water level. So how we got some of that data is from surveying the entrance channel. This is just the change in cross section. So if you were to walk across the entrance and survey that there, but this is just the first 2 hours. After that, it got way too fast flowing. And so we just measured by shooting a laser pointer across it. But essentially, those three stages relate to what's happening in terms of drainage and processes in the basin. And so we're starting to combine data from a bunch of different estuaries around Victoria. We're aiming to capture some natural openings in there as well to compare between natural and artificial ones. And trying to think about, can we use change at the mouth to predict drainage rates and what's happening in the basin. So just a few take-home points. Whether these estuaries are open or closed is a function of wave energy or power versus stream power, and also the tidal currents going out with the ebbing tide. Compared to other estuaries in Victoria, Curdies is quite large in terms of its basin area. It's not super infilled and it has a big tidal prism. So that means that we tend to get openings that are weeks to months in duration instead of just days to weeks. And it's also highly seasonal. And in terms of the research we've been doing, we're really trying to kind of build on this data set so we can get a good representation of what's happening across different sites. But we think we can start to use this data to predict when openings will stay open after excavation, how long they'll stay open for, both for natural and artificial openings, and then how change at the mouth impacts on processes in the basin. Thank you.